Hello guys, welcome to Ramta Solutions. Today, as we continue with our series on work, energy and power, we are looking at the second part of the work done by a non-conservative force, right? We are looking at the second part of the work done by a non-conservative force. Now, in the first part, we have defined conservative and non-conservative forces. We also we showed you the effect of the work done by a conservative force. Now in this video, we are going to look at the work done by a non-conservative force. So as you can see, this is the work done by a non-conservative force. So let me just write it here. This is work done by a non-conservative force, right? This is work done by a non-conservative force. All right. So this work done by a non-conservative force, we defined what is a non-conservative force. We said this is force for which its work done on the object depends on the path taken. I will also show you the definition of work done by the non-conservative force with regard to the network. Okay, I will also show you what it means, because in the first video we showed you that work done by a conservative force, the network done by a conservative force is zero. But here we must see if it's zero or it's non-zero. So wait and see. So I will give you an example. So consider the path of an object, of an object moving up and down the ramp, experiencing friction, experiencing 15 Newton frictional force. Frictional force. Consider the path of an object moving up and down the ramp experiencing 15 Newton frictional force over 3 meters, right? Over 3 meters. So here we are. This is our ramp. Now this ramp is 3 meters. Now let's say this is our object here. Let me put it somewhere here. Let's say this is our object here. As it goes up, friction is obviously opposing motion. As it goes down, the blue one represents going down. Friction is always opposing motion, right? Friction is always opposing motion. So for this one here, it goes down. For this one here, the object goes up. Okay, so I only drew this to help you make sense of it. Okay, to help you make sense of it. Remember, the path is 3 meters. Now let's calculate the work done by friction in moving the object up the ramp. Okay, so we will say work done, let me put it as W sub F, meaning work done by friction, is equal to force of friction delta X cos theta. I should have written upwards or up the ramp. So okay, so what is the friction? The frictional force was 15 newtons. The distance was 3 meters. Obviously, friction always opposes motion, so the angle between the force and the displacement is always 180 degrees. Right? So this is negative 45 joules. Now check when the object goes down. When the object goes down the ramp, what's happening? Again, W sub F is equal to F sub F delta X cos theta. Again, when the object moves down the ramp, friction will be in the opposite direction, right? So it's still 15 times 3 times cos 180 degrees. So what is this? This is negative 45 joules. Now, what is the net work done? The net work done is basically, let's call it work done to move the object up plus work done to move the object down. What is it? It is negative 45 joules plus minus 45 joules. So our answer is negative 90 joules. Can you see that? So as you can see now, the net work done by a non-conservative force is not equal to 0. Okay? The net work done by a non-conservative force is equal to 0. So we can therefore define a non-conservative force. We can also define it as non-conservative force. We can also define it as force for which, let's say, force for which its net work done is not 0. It's not 0. Remember, we have also defined that the work done, the non-conservative force in the previous video, we defined it as force for which the work done on the object depends on the path taken. Another definition could be or is force for which its net work done is not 0. Okay? You have seen that. Work done by a non-conservative force is not equal to 0. Okay? It is not equal to 0. Alright? So, remember, we mentioned what are your conservative forces and what are your non-conservative forces. Alright? So, again, remember, when a non-conservative force is acting, mechanical energy will not be conserved. Alright? When a non-conservative force is acting on an object, mechanical energy will not be conserved. Alright? So maybe let me write that. When I want to call it NC, non-conservative, when a non-conservative force acts on an object or on a system, okay, on an object, mechanical energy is not conserved. Okay? Mechanical energy is not conserved. Right. So what is happening here is that we are basically saying mechanical energy before is basically greater than mechanical energy after. Okay? It's basically equal to mechanical energy after. But we know energy is always conserved, right? Energy is always conserved. So we have to include the work term. Okay? We have to include the work term. So what we can say, okay, this is equal to EM of F minus work done by a non-conservative force. Right? We can say this is initial mechanical energy is equal to final mechanical energy minus work done by a non-conservative force. So this WNC is work done by a non-conservative force. By a non-conservative force. Oh, this word is too long. I'm sorry. I can't be writing it over and over. However, you are permitted to write W sub NC. That's your work done by a non-conservative force. Okay? So, now, you know what is mechanical energy. Alright? So now let's simplify this. Let's expand it. In the next page, we said EM initial. So this is basically EK initial. Alright, let me maybe write it like this. EK initial plus EP initial is equal to, we said EM final. So this is EK final plus EP final. Remember, mechanical energy is the sum of the object's kinetic and potential energy minus work done by a non-conservative force. Further, we therefore say work done by a non-conservative force is equal to Kf plus Kp minus Ki minus EKP. No, EPI EPI, right? So further, you can see that we have final kinetic energy minus initial kinetic energy. This tells you what change in kinetic energy plus change in potential energy. Can you see that? EK final minus EK initial. EP final minus EP initial. So work done by a non-conservative force is equal to change in kinetic energy plus change in potential energy. This is the formula that you use when you want to find, maybe let's say, we will do examples, but when you want to find any of whatever parameters you need in this expression, okay? So you use this formula only when you have a non-conservative force, okay? You use this formula only when you have a non-conservative force. Are we clear? There is another way of solving this, but we're not really going to look at it. There is another way of solving this, but we're not going to look at it. Okay? So, now let's try something. Okay, let's try something. Let me see what we can try. Or I should let you wait for examples. Nah, I'm not gonna make you wait for examples. So we're going to try an example here. Okay, we're going to try an example here. So this is an example from your Solutions for All textbook. Okay, so it's like this, and they say I'm gonna put a person here, an object. So I'm just gonna put a block. So this is point A, while this is point B. Okay, and this is the height for point. It's called height H. We don't know what it is. And then they say the distance here is. They say the distance here is 10 meters. In addition, initial velocity, which is velocity at point A, is 6 meters per second, right? And the object or the person is weighing 70 kilogram. And then this angle here is 30 degrees. Maybe let me write it here. It's 30 degrees. That's the angle that surface makes. It's an inclined surface. Now, in addition, they say this person was skating, was skateboarding, so he's skating down the slope, okay? And he experiences a frictional force of 190 newtons, right? He experiences a frictional force of 190 newtons. The first question says, hear me, the first question says, calculate, let's do this. The first, calculate, I hope you took this with me. So the first question says, calculate the gravitational potential energy at point A. So calculate gravitational potential energy at point A. And then the second question says, calculate the speed of the person at the bottom of the slope. So meaning calculate VB. Okay? Meaning calculate VB. Okay? So let me wait for you to take this information and then I'll move to the next page. Okay? I'll wait for you. Remember, this is one interesting formula. I like using this formula. Whenever I make my calculations, I know using it, work done by a non-conservative force. When I use it, I never go wrong. But I will explain what you really need to do when you consider using that formula. Okay, you guys are done? So for the first part, it says calculate the potential energy at point A. What you need to see is this, is that you don't have your height, all right? I'm going to draw a right angle triangle. Your height is not given. You are given the side here, which they say is 10 meters, and the angle here is 30 meters. It's 30 degrees, right? So you need to know what your height is, and the height is opposite to the angle. So what is your height? So basically you're saying sine 30 degrees is equal to height over 10. This therefore implies, by the way, it's number 1. This therefore implies height is equal to 10 sine 30 degrees. I think you can say this is 5 meters, right? Because sine 30 is half, right? Now, you are now looking for potential energy at point A. All right, what is potential energy at point A? It's it's mgh, right? Potential energy is mgh at point A, of course, right? So, what is it? What is the mass of the object? It is 70. Gravitational acceleration is 9.8, and the height we just calculated it to be 5. Now, let's see. We have 70 times 9.8 times 5. So this is 3,430 joules. Okay? 3,430 joules. Right? Okay. So now let's head to number 2. Number 2, we realize that for this motion, we have friction that's taking part. So we can use what is that? We can use, remind me please, we can't use law of conservation of mechanical energy, because it is not only gravity that's affecting motion, even friction. So we can use work done by a non-conservative force. So let's get into it. So work done by a non-conservative force is equal to change in kinetic energy plus change in potential energy. This basically tells us that we are using which force? The force of friction, delta x cos theta. Allow me to say half mv b squared minus half mv a squared, right? This is final velocity, this is initial velocity, plus mgh at point B minus mgh at point A, right? Now, what is our frictional force? They gave us the value of our frictional force. They said it is 190 newtons. The distance, it was 10 meters. And obviously, friction is always opposite the motion. So it is 180 degrees. Half times, what is the mass? It's 70. Velocity at point B, we do not know it, so I'm going to leave it like this. Velocity at point A, I think they said it was 6 meters. Yes, it was 6 meters per second. So it will be half 70 times 6 squared. Height at point B is 0. Right at point B, our height is 0. So we can just write this part here to be 0. While this part, we got it, which was potential energy at point A, we got it, it was 3430. Right, 3430. Right. Okay. So we have here 190 multiplied by 10. Right, we have 190 multiplied by 10. It is 1,900. Oh, it's negative 1,900. Remember, 190 multiplied by 10 multiplied by cos 180 degrees. It's minus 1,900. Do not make a mistake of forgetting this part. So here we have half of 70, which is 35 v sub b squared. And let's see. 35 times 36. This is minus 1,260 minus 3,430. Okay, minus 3,430. So let's see. We have our answer plus 1,260 minus 1,900. Right? Therefore, 30 plus. So our answer is, let me see, 1000 negative 1900 plus 1000. Okay, maybe let me write it like this. Okay, let me write it like this. 260 plus 3430 is equal to 35 VP squared. So this is 2790 is equal to 35 V sub B squared. Dividing by 35, this will be let me see, 2790 divided by 35 is, this is 79.71428571 is equal to V sub B squared. Now find the square root of your answer. So on my calculator, just say square root answer. Our answer is 8.93. Our answer is 8.93 meters per second. So this is the speed of this person at point B, right? And this is how you calculate work done by a non-conservative force. Remember, if you have more than one non-conservative force, include them. For example, you will be having applied force, include it. You will be having applied force and you will also be having friction. Include them in your non-conservative work done by a non-conservative part, right? So in this part, include for all the forces that are not conservative forces, okay? And you will never go wrong. Right. So in conclusion, let me say this, guys. Work done, let me go back to my color. Work done by a non-conservative force is equal to change in kinetic energy plus change in potential energy. This works when you have forces other than gravity. Okay, when you have your friction, applied force, and so on. This is when you can use this formula. Because if you have only gravity affecting your motion, this will be zero. Okay, this will be zero, and this will be becoming your law of conservation of mechanical energy. So remember, use this equation only when you have non-conservative forces. Okay, only when you have non-conservative forces. Remember, non-conservative forces are those whom their total work done is not equal to zero. Okay, I have showed you here that the work done by a non-conservative force is not equal to zero. Can you guys see that? And the definition, force for which its net work is not zero. Right. So with that being said, it's a wrap. I will see you next time, and stay tuned for more examples. Again, when I see you next time, I am seeing you for power. So this is it, guys, and salam sink. Bye-bye.